Spend most of today's class in Visual Studio, right? And I have lots of code that we'll do. We'll use the Visual Studio debugger to see what's happening with the physics engine, and then I have just a couple of little exercises for you guys to do that will be quite good. So Darren's not here, or not Darren. Yeah. Well, anyway, just with regard to limits on joints, Hao Guan, who did the ragdoll, the capsule ragdoll from last year, will be here next Wednesday. So he's doing a master's in Trinity at the moment, and he's extremely busy. So this is one chance. If you have any problems with code for your assignment, this is your one chance to ask somebody who got like 100% in this assignment last year how he did anything on the assignment. And he's so busy that like he's literally going to come here for probably an hour on Wednesday, and then that's it. Okay, so you need to be here next Wednesday if you want to make use of his brain power and have an idea about what you want to do for your assignment, so you can ask him. Is that clear to everybody? So he's doing us a favour by coming, and so just make sure you're here next Wednesday for the lab class to ask him. Okay. Yeah. So if you guys remember what we were will we quickly go through the Hamiltonian mechanics from last week, just as a small bit of revision before we start talking about physics engines, because I know some people weren't here, and I think it's just no hard to revise, what the Hamiltonian mechanics is before we start using the physics engine to do the integration for us. So guys, can you look up from your laptops just for a little while? And let's just remember, most game engines now, BGE is the same, right? And it's modeled on Unity to a certain extent, right? Has an object called a transform object. And I presume that Unreal Engine, those of you that are using it, does it have something equivalent? Okay, so the transform object is going to encapsulate the position, orientation, and scaling for an object in the scene. So the transform object, everything that you see in a game has a transform object that controls all of that kind of stuff, right? And the transform object is going to contain stuff like the position. For the orientation, obviously it's going to be a vector. For the orientation of the object?
Oh, sorry.
Quaternion. Okay, so we've got a quaternion to represent the object's orientation in 3D space. The position is very simple, it's just x, y, and z component. The quaternion being the w, x, y, and z component can generate a quaternion from an axis of rotation and an angle of rotation. If the object is not rotated, its quaternion is the, which quaternion? Here. No, get the term right now. It's called the identity quaternion, okay, called the identity quaternion, right? So that means no rotation, and then you can generate a quaternion to represent the orientation of an object. So if an object is like a BGE, most objects point down the negative z axis, that's their identity quaternion. And then if they rotate, so for example, if it's rotating 90 degrees around the y-axis, that's a 90-degree yaw. You calculate the quaternion, set the object's transform quaternion to be that rotation, and eventually that's going to get multiplied into the objects. The other thing that the transform encapsulates. So in order to draw it, we need a... No, we need what to draw it? So, what's that?
The model.
Yeah, to model is, okay, of course you need the model, but to draw it, like what's required mathematically to draw something in 3D? Yeah, the matrix. So the object's world transform matrix. So the position, the quaternion, and another thing which is actually the scale. These three things get together. Each one of those gets transformed into a matrix, a 4x4 matrix. The three of those 4x4 matrices are multiplied together into the object's world transform. So that's a 4x4 matrix that gets passed into what kind of a program? What kind of a program is used for rendering? So we pass in all the vertices, and we pass in also this thing into what? Something that runs on the GPU. What are programs that run on the GPUs? Into the shader. Okay, so all of the stuff gets passed into the shader. The shader will then take each one of those vertices, multiplied by the world transform, and then it ends up being in... Sorry, it gets multiplied by the world, the view, and the projection transform matrix, or the world is also known as the model matrix, but basically gets multiplied by those three matrices, and it ends up in 2D space on the screen. That's what the shaders do, right? So all this stuff is in the transform. Position, quaternion, scale, and world. Actually, BGE has a few other things thrown in there as well. Stuff like the velocity of the object. And it also has stuff like the diffuse, colour, the specular. And again, all of these are passed into the shader and are used to do lighting calculations. And the ambient. So that's the transform. Okay, is there anything else that's in the transform? I don't think so. But most of these things, by the way, aren't in transforms in Unity and Unreal Engine. These are just things I've added to BGE because I don't have game objects in BGE. So, yeah. So then we talked about integrating. What does integration mean? When does integration happen in BGE? What method controls or what member function is integration all about? What does integration mean? Can you tell me?
For rotations, getting stages.
It's for anything. You're thinking of interpolation. Okay? Just integrate. If I say integrate that object, what does that technically refer to? Mathematically, or in terms of the engine, what does it refer to integrate the object? What's the member function that controls integration? Do you guys know? Integration just means what? Updating with respect to time. Okay, so it just means a time delta elapses, and you then calculate the new state of all of this. Again, that's called integration. So it just means updating with respect to time. The method, the member function that does it is the update method. So update is called once per frame. You need to know the time delta, which you get from the time static field, the time delta static field in the time class. That tells you how much time has elapsed since the update method was, or the member function was previously called. And you update the new position and update the new quaternion based on whatever forces have been applied to the object or keys that have pressed and stuff like that. So that's called integrate. And then you get new versions, new values for position, quaternion, scale, velocity, and so on. So, sorry, is there anything else? Position, scale. No, that's it. Okay, we say to do, like the thing you guys had to do on Tuesday was basically an Euler integrator, okay? So the Euler integrator is just like a 2D integration that we want to do. If I just want to do a 2D integration for each one of these things, then I need a couple of extra variables. So first of all, obviously you have the time delta, which I think I call delta time, because that's what Unity calls it. So I have Unity, delta time. What are the other two variables I need in addition to velocity, position, quaternion, scale, world? There's two extra things you need to do. You need theta. Yeah, we possibly might use theta. But there's two other things. In order to do physics integration, you need two other things to calculate. Calculate the force. Okay, so we have an extra thing called force. And we have an extra thing which is the yeah, just for 2D, right, for Euler. We have an extra one called the, what does force cause? Do you remember? Force causes acceleration. Okay, so we calculate some forces, some keys are pressed, we apply some forces. What happens to that? If I press, for example, the forward key, what do I want to do to that force variable? Increase if I wanted to move. I want to increase it, sure. So I'm going to add to that force variable. And what do I add to the force variable if I wanted to move, you know, if I press my forward? Acceleration is calculated from force.
Acceleration along the look vector.
So, exactly, I add force in the direction of the look vector. So if I wanted to go forward, I take the look vector, I multiply by some scalar number. What's the scalar number I multiply it by? What's the unit of measurement for the scalar I multiply it by? You guys remember? What's the unit of measurement for force? No, joules is energy, so force is newtons. Okay, so I take the forward vector. For example, if I wanted to push the thing forward, I take the forward vector multiplied by the look vector. So you take the look vector, you multiply by how many newtons of force you want to get. The look vector, obviously, what's the length of the look vector? What's the size of the look vector? 1. So it's 1. If I want to apply 10 units of force, I take 10 multiplied by the look vector. So that takes the look vector, so the force has got the same direction, but now it's scaled by 10. So I'm taking 10 units of the look vector. I'm adding it to the force accumulator. So I'm going to take the force and I'm going to add 10 units of force in the direction that the object is looking. That's if I wanted to go forward. Similarly, if I wanted to go left or right, I'm going to take the left vector or the right vector, or minus the left vector. You know? So that's the first bit. So force in the direction of the look vector. This other thing here is the newtons of force. You multiply the two together and you add them to this force accumulator. So the forces are all added in a moment. Press the key, a certain amount of force is added for the duration of that. For the duration of that update, there's some force applied, right? So the equations to do the Euler integration, we have acceleration and force. By the way, are these vectors or scalars? Vectors. They're all going to be vectors. Okay, apart from the newtons, this is going to be a scalar quantity. The look vector is a vector. Force is a vector, obviously, because you can have force as a direction. Anything with a direction is a vector. And acceleration, similarly, is a vector quantity. Okay. So, first thing we do is we take the acceleration and we calculate it from the force. What's the equation for calculating the acceleration from the force? Acceleration equals. Acceleration is going to cause some change in velocity eventually, but acceleration from the force. I apply some force. Yeah, so I take the amount of force and I divide by the mass of the object, and that tells me how much acceleration that force has caused. Right, so I'll think about it. Obviously, a big heavy object, you apply some force to it, it's going to move a small amount. If you take a light object and you apply the same force to it, it will move a large amount. So acceleration equals the force over the mass. The next one then that I calculate is the velocity. So velocity plus equals to what?
Acceleration by...
Yeah, acceleration multiplied by the time delta. Alright, so for how long the amount of acceleration is being applied for, that's going to cause a change in velocity. So I add the amount of acceleration to the velocity, and then finally I take the position plus equals to velocity multiplied by time delta. And those three equations allow you to implement what's called an Euler integrator. That's the three equations of motion for 2D physics games. Okay, so the 2D physics game I showed you guys last week, which I can show you again. Maybe if I get a minute, I'll show it to you, just to show you how you can, let's see, I might need to get a battery for that. No, put batteries in it, I'll show it to you. You can do any kind of 2D physics using these three equations, alright? Now, there's a couple of other little things that we might want to do. Thing number one, okay, this is 2D physics, okay? Let's do thing number one. What happens to the force accumulator each frame?
Reset.
We reset the force accumulator. So after you do this, you have to remember that if you're adding a load of forces in up here, you have to remember to set the force back to 0. So you set your force accumulator vector back to be the 0 vector at the end of the Euler integration. And that's like saying, press my thrusters, the force is only applied so long as that is pressed. Otherwise, what's happening here is I'm continually applying the force. And if you forget to reset the force accumulator, your object will continue to accelerate. So we have to reset the force accumulator. Last thing, how do I calculate the object's look vector? Or is there a way in 2D to basically consider the look vector, and what way the object should point? What do you think? So the look vector is going to determine the rotation, and even looking at the theta version of the rotation, is there something we can do with this thing? Say I'm pressing left arrow, right arrow, I'm applying forces all over the place. Is there anything I can do to calculate the object's look vector? Or is there anything that might make the object kind of, rotate in a particular way based on the forces?
The unit circle. The unit circle.
The unit circle. Yeah, thinking about it, actually we might use the unit circle, but is there a simpler way? And you might kind of realize this, but this is how all simple 2D steering things work. If you look at Craig Reynolds' steering behaviors, it does this little trick at the end. So here if I basically say this, and if I basically constrain it like this, and I say that the object always looks in the direction it's traveling, does that tell you how we might calculate the look vector? Forward. Yeah, cool. So what do we do with the look vector? What do we do with velocity to get the look vector from it? Yeah. Normalize. Is that the word you're looking for? Yeah. So we just take the look vector equals to the velocity divided by the length of the velocity vector. And that's just a trick. Not all games do this, but simple steering behaviors, we'll do this in the second semester. We'll take the look vector and generate it from the velocity vector. So that just means that if you're traveling 10 kilometers a second in this direction, calculate your look vector and rotate your object so that it always looks in the direction in which it's traveling. Of course, this is just a trick, and it's not how things move in the real world. And if you make this constraint here, what's the big limitation of doing this way? And there's kind of an obvious limitation of doing this.
You don't know where it's looking when it's sitting still.
What's that?
You don't know where it's looking if it's sitting still.
That's okay. We just presume that it's whatever it previously was looking, it's going to stay looking. But what's the other problem with this? Is there certain types of physics that we can't implement if we do that? You got it. Yeah, this means you're always looking in the direction in which you're traveling. Do you follow? So like, it just, you can't do things like have your object looked in that direction but move in that direction if you do that little trick. Is that okay? Because you're just basically calculating the velocity, calculating the look vector from the velocity, so that's why you can't do it. Is that red light on that camera?
Yeah, it's recording it.
Okay, cool. So, that's 2D physics. Is everybody okay with 2D physics? So using 2D physics, you can make Space Wars, like the game that I showed you guys last week. Did you remember it? Or?
Yeah.
Yeah, so that's the Space Wars game, and you can do 2D physics. Here's a quick one for you, right? A couple of interesting things in Space War that I discovered, and I had a little bit of a little kind of a breakthrough. It's maybe worth considering. I'll show it to you. Maybe you'll figure this out yourself, and maybe it's obvious to you. So I was tweaking Space War, right? And there's a couple of things I was tweaking about it to try and change the gameplay a little bit and make it a bit more fun to play. So here's Space War. I just have one controller, right? So I'll just show you with one controller. I don't have a second controller today, okay? So it doesn't really matter. It's just there was a couple of sort of gameplay things that I wasn't entirely happy with, and then I tweaked the numbers. And I wasn't quite sure what I was doing when I tweaked the numbers, but when I thought of it, it kind of became obvious to me what was happening. So first of all, if I run Space War, okay, and I'll just spawn one guy into the scene here. Turn this down a little bit. Oh God. Sorry, it'll crash. What's wrong here? I actually had some weird Git problems earlier. I think this is one of them. I think I may have deleted some of my audio files. Let me have a quick look here while you ask. No, they're all there. So what's the new player doing? Sorry, it's just the little audio file. It's one of the files. Care about the creating file loader object. No, that's just a sound error. If I just comment these guys out, just get the game with no audio. So the game with no audio, right? Just this way. Okay, here's my player. So yeah, I changed a couple of numbers, and you guys might kind of realize. So there's the player. So one thing I was kind of curious about was, would I, there was a couple of numbers that I changed, right? This is basically the forward Euler integrator. It doesn't do this last step here. It actually controls the look vector using a different variable. But say that guy there. So I changed, one thing I was kind of concerned about was the object was, say, getting really close to that, and I was finding that I was unable to escape the force of gravity in this game. I'm just wondering, would you guys happen to know what number would I needed to have changed to basically make it? So now you can see I can get right in and I can still apply thrust and I'm able to get out. What number would I have had to change to make that possible?
Amount of force.
Okay, so there's thing number one, the amount of force that applies when I press the thrust button. So the number of newtons of force. Huh?
You can change your mass.
Yeah, definitely. That's exactly what I did. So I changed the mass of the object. So if I make the mass of the object smaller, I don't have to adjust the force. Now the other thing that I was kind of curious about, I don't know why this took me so long to realize, what about the force of gravity? How do you think gravity is calculated?
The 0 is the middle of the spiral.
Okay, so there's a position that represents the center of the screen, and there's a position of that guy, and then each frame I'm doing something to apply gravity. And I guess you can probably realize that when I'm quite far away,
That's gravity.
So you have a function that's applying force to everything around the sun, drawing it towards it.
Sure.
And a scalar saying it fades off as you get further away.
okay, so that's not a bad first attempt, right? You've kind of captured a lot of what I need to do, but it's not quite right either. Okay, so think about it first of all. First question. If I change the mass of that object, does it affect gravity? Or should it affect gravity? So that was the first thing that I kind of was slightly realizing. I was changing the mass of the object and going, hey, it's way easier to play now. I've obviously changed the amount of gravity that's been calculated, and that's not right. But obviously, you know, it doesn't matter what mass the object is. Sure it doesn't? It doesn't matter what mass the object is, because gravity is not affected by mass. In actual fact, more force is applied. You know, we realize this when we think about gravity, right? Think about gravity. A heavy object, an object with lots of mass has lots of gravity. That's why that object falls at the same speed as an object with not much gravity. So first of all, changing the mass of the object doesn't affect gravity at all. What is gravity? Or has a simple way to do gravity then? So first of all, gravity, if you want to take out the force bit, you can implement gravity using just what? Just which two equations up there?
The velocity and the momentum.
So this one and this one.
Yeah.
Okay. So you don't even talk about forces. If you want, you can calculate what force of gravity based on the mass. You just rearrange this equation here. If I want to have, for example, on Earth, we have 9.8 units of acceleration. Okay, 9.8 is acceleration due to the force. So I just want to rewrite this equation in terms of force. To rewrite this equation in terms of force, what do you just calculate? And you would just basically say, I want to get force on one side. So let's multiply both sides by mass. And then you get A times M equals the force. Is that right? Have I done that right? Yeah, so you just take the rate of acceleration multiplied by mass, and then that tells you the object. And you can do that extra stage. But a simpler thing to do is just to do these two equations here and not bother calculating the force. Alright, so, you know, all you need to do is just take the coefficient of acceleration, the rate of acceleration, and just make sure you do this every frame. And then don't even bother calculating the force. Yeah, but you can, if you want, you can calculate the force like that. Yeah, I don't know. That's kind of it. I don't know if there's something else I need to say about physics.
How would that reduce gravity over distance?
What's that? Oh yeah, gravity over distance. You tell me.
The distance between the sun and the position.
Yeah.
Being
It's actually kind of simple when you think about it. In other words, I just want to apply, Jesus, maybe I need to double check myself, but I wrote it, but I can't quite remember. Apply gravity. I'm going to unplug this thing for a second. Oh yeah, okay, so it's fine. Yeah. So how do I do gravity? How do I do gravity based on the distance? And as you can imagine, the distance is, it's the further away you are, the less gravity you want to apply. How would you do that?
Should we use the XY coordinates with the object?
You have the XY coordinates of the object, you have the XY coordinates of the planet. Yeah.
Take the distance between them, and the longer the greater the distance.
What's the maths of doing that to say basically the farther away it is, the less you apply? What's that? Divide what by what? Yeah, so we just previously said we're not going to even use force. We'll fake the gravity without doing the force. But we could do the force. But even if you did do the force, what you'd want to do is take this force and you'd want to scale it by the distance. But you want to say the further away it is, the less it is. So the bigger the distance, the smaller the force. How do you write that mathematically?
1 over the distance.
Okay, thank you. It's 1 over the distance. And you can change this number on the top, or you can multiply it by some scalar value, but obviously it's 1 over the distance. If the distance was 0, then what would you have? 0 into anything is... What's 0 into anything? If you take 0 into 1, what do you get? Huh? Infinity, okay? And if you take like a big number for distance, then it's going to be a really small number because you're dividing up 1 over. So it's the inverse of the distance. That's basically the calculation, okay? So that's how gravity works. You just take the inverse of the distance, multiply by the coefficient of gravity, and then you're basically doing gravity. That's how gravity works. Simple as that. In a 2D little game like that. Okay, so we had all of these things for doing Euler integration, and then last week we added a whole load of extra equations for doing Hamiltonian integration, which is integration using quaternions and rotation. So to our calculation, we're going to add a few extra things here. We've got force, we've got acceleration, we've got time delta. What are the extra ones we need to add to do 3D physics? So we need to add a whole load of extra variables to do integration using 3D physics, in addition to all of these ones. Okay, let's think about it, right? So an object is moving. An object can also rotate and not move. So what's the variable that controls the speed of rotation? What do we call that? It's called the... Huh? No, the speed of rotation, it's called the angular velocity, right? So the angular velocity is the variable that controls the speed of rotation. Which I refer to, I think, as AV for angular velocity, right? So angular velocity, is it a vector or scalar?
Vector.
It's a vector. Okay, what's the unit of measurement for angular velocity?
Radians per second.
Radians per second. Okay, so the angular velocity, we also have angular acceleration, which is given in what? Radians per second, or degrees per second, okay? The sort of rotational equivalent of force, what's that called?
Torque.
It's called torque, all right? So torque is like a rotational force. So angular velocity, angular acceleration, and torque. Okay, so then we have a load of equations to sort of integrate these in the Hamiltonian integrator, okay, so that we can do full 3D physics. So the first one is to calculate the torque from the force. Torque is going to be equal to what? You guys remember? Torque equals... Sure. So torque equals the position where the force is applied relative to the center of mass of the object, crossed with the amount of force. So, you know, thinking about this spaceship here, you know, this spaceship can rotate around obviously 360 degrees, you know, or any kind of things. If you apply your force in this direction, this is the direction of the force, and this is how it is relative to the center of mass of the object, it's going to move forward, right? You know, so that's taking the cross product of this vector with this is the force vector, and this is the torque. Sorry, this is the relative position, and this is the force. So when you cross those two together, what are you going to get? That's an interesting question. Because this is the center of mass of the object. In fact, it's going to rotate a little bit this way, because you're going to get a bit of torque. Yeah, think about it. If you just do this thrust here, okay, just one of the nacelles, you're looking at it from this angle. If you just thrust here, you know, you're taking the center of the mass of the object. Maybe the center of the mass of the object might be the center of the saucer section, right? If you just thrust one of these nacelles, you're going to get this vector here. The other vector then is the direction. So that's the direction, and you cross it with that one. This is the axis of rotation, so the thing is going to start to rotate in this direction. So you cross this thing. If you do both of them at the same time and sum them, you're going to get forward. You're going to get forward movement. So that's the first equation, right? The second equation then is looking at how the angular acceleration. Angular acceleration then is going to be equal to, do you guys remember angular acceleration? And we actually have another variable here.
4 times the inverse of the inertial tensor.
So it's the torque multiplied by 1 over the inertial tensor. I don't know why that is. It doesn't make a lot of logical sense, but that's basically the equation. The angular acceleration is equal to the torque multiplied by 1 over the inertial tensor. What's the inertial tensor? What type is it?
3x3 matrix.
3x3 matrix, which describes the shape of the object, right? And you look up inertial tensors in an inertial tensor table, and you can approximate differently shaped objects by just saying it's closest to a box or, that sort of thing. So it's a 3x3 matrix. You've got this extra equation, right? And then we have angular velocity is equals to angular velocity plus the angular acceleration multiplied by the time delta. And then finally, we have this equation which tells us what way the object is going to be oriented, which is the last equation. So the orientation quaternion of the object, I'll just put this up here, the orientation quaternion of the object is going to be equal to the orientation quaternion of the object plus the time delta over 2 times W times O. And that's the last equation for implementing 3D physics. So the old orientation of the new orientation is equal to the old orientation plus the time delta over 2 times W, where W is the pure quaternion made from the angular velocity. And we set the, does it say W component? The x, y, and z component obviously comes from the x, y, and z components of the vector. The w component, Simon, do you know, or do you remember, is it 1 or 0?
I think it's 1.
I think it's 1, is it? Because I actually haven't got it on my notes, but I'm sure I have it in my code. I'm sure I have it in the code somewhere. W. Oh, I have it as 0 in my code, and it seems to work, so I think it might be 0. It might be 0. If it's 1, maybe 1 works as well. But set the W component of the W quaternion here. So you make this from the angular velocity. When you look at the code, like the code is the code is basically just an implementation of those set of equations, right? And I have a controller here called a steerable 3D controller. When we look at the steerable 3D controller, and we look at, first of all, that's calculate inertial tensor. And again, this equation, or this way of calculating the inertial tensor, I looked it up on Wikipedia. Right, so it gives you loads of inertial tensor tables for differently shaped objects. And I just calculate a box-shaped inertial tensor, regardless of what kind of rigid body is passed in. Okay, and I calculate it based on just the bounds of the object. And you set the numbers that go down the diagonal of the 3x3 matrix. And you look up that equation, it tells you it's like the mass plus, the height multiplied to the power of 2 plus the depth. Anyway, it's just a little equation. You look it up on Wikipedia. That tells you how to calculate inertial tensor tables. And then the integration, I'm not even 100% sure this is correct, but it works. So the angular acceleration equals the torque multiplied by the inverse of the inertial tensor. So that's that equation there. And then the next thing is angular velocity equals angular velocity plus angular acceleration multiplied by the time delta. Next thing, this here, what's this doing, by the way? Angular velocity multiplied by equals to 0.9f. What do we call that? It's just damping, just slows down the angular velocity, right? And then I'm making my W quaternion here, setting W component to be 0, the x, y, and z from the angular velocity, and then the orientation is equal to the old orientation plus W multiplied by time delta over 2 multiplied by the transform orientation. So that's literally that last equation there. And then I finally normalize it just to make sure that the final quaternion is normalized. And that seems to work. You can do 3D physics using that, okay? So that's 3D physics. That's basically all the stuff that we did last week. So anyway, hopefully you guys get the idea of, using equations of motion to simulate these things. And you understand what all of these things refer to and how you apply torque. Torque is, if you think about torque has got 2 components. It has the direction and the amount of torque. When you're applying torque to an object, you always do it perpendicular to the direction in which you want to rotate. So if you want the thing to go forward, and you've got a wheel here, then this is the way you apply your torque. You apply your torque along this vector here. Does that make sense to everybody? Alright, so that's all of the kind of stuff. From here on in, we'll use the physics engine to do all of these calculations. Are you guys ready to start talking about physics engines? Or do you want to take a short break? Huh? Let's take a 5-minute break. Okay, and then we'll come back and talk about physics engines.